Can you see my screen?
Yes, yes,
okay.
You can see it. So this is the last talk of this section. Is from Thomas Grandittis, who is now in Graz, and he was previously in Lugano. He will give a talk about the entitled Geodesic-based earliest activation sites identification in cardiac models. So please, Thomas, the floor is yours.
Okay, so thank you for the introduction, and also thank you for having me here. It's always a pleasure. So also a big shout out to my co-authors, especially Alexander Effland and Simone Pizzuto, who were really helpful in conducting this study. So what are earliest activation sites and why would you need them? So of course, these are earliest activation sites in cardiac electrophysiological models. So as you already know, ventricular activation heavily relies on something called the Purkinje network for electrical activation, which quickly propagates the electrical activation throughout the ventricles and the myocardium. And you can think of these entry points, so the entry points that connect the Purkinje network to the myocardium, as discrete earliest activation sites, so directly boundary conditions. And an important observation is, so this set of earliest activation sites is not detectable in vivo, or it's very difficult to do so. And you can also think that in severe pathological conditions, this actually corresponds to a faulty set of earliest activation sites. So from all of this, you can already conclude that it's very important to know these earliest activation sites, but there are only a few works out there that really deal with this topic. And we propose a method called GEASI that can fit these parameters using an iconal model to several clinical recordings, mostly electroanatomical mapping, but also the ECG later on. So like I said, we use the anisotropic iconal model. So you compute from the conduction velocity tensor D the activation times on the whole cardiac model phi E, and it's given by this PDE. And what we actually want to find are the earliest activation sites given by this set E, which is defined by the number, the cardinality of the set, the location xi, and the timing, so at which point they actually initiate the activation. D is actually a positive symmetric definite tensor, and also it is bounded, so it is not between, it has some finite conduction velocity. That's the only thing we're assuming for now. So directly optimizing the earliest activation sites from this equation is difficult, so actually we propose that we recast this problem in terms of its Helmholtz-Jacobi formulation. So in this formulation, you do not solve the PDE above, you instead solve an ODE, which is basically you take each point on the domain has its activation time defined by the time it takes to travel to the earliest activation sites by this geodesic distance, or this so-called geodesic distance delta, plus the initial timing that you have at this point. And this is defined by this equation. It's not so important that you know it, but basically you take the shortest path of all possible paths between 2 points x and y, where y is actually our earliest activation site. And the length functional is actually defined by this metric d, conduction velocity. So here's some little example if you have troubles visualizing this. So on the left, you can see the isotropic conduction velocity. So yellow are larger or higher conduction velocities, and you can compute the anisotropic iconal equation, which gives you these contour lines as activation times. But you can also think the activation time at this point is basically the time it takes to travel along the geodesic in red here. So what we're doing here is actually we're recasting the problem from a PDE into a series of ordinary differential equations. And the nice thing, or maybe it's a neutral thing, is it's potentially mesh-free, so you can choose the order of the solution that you want. And so it's also independent of the polynomial space on which you discretize. And now the important thing is we're using a gradient-based approach, which have been shown to be more efficient. And the gradient of this geodesic distance is given by the logarithmic map, in this case, like the equation you can see here. I'm not going too much into detail since we do not have much time, but actually this is a consequence of the first variation of arc length, which is a common topic in differential geometry. So you can see these results are actually very old, but nice thing is the application to cardiac activation here. And the nice thing is also it's smooth. well defined almost everywhere. And I will show you later what I mean with almost everywhere. So actually, if we have multiple earliest activation sites, then we simply need to define something called regions of influence. So you can really think of this as a one-to-one correspondence. Each earliest activation site exactly activates several points on the domain, but each point is uniquely assigned to one earliest activation site, except for boundary cases where you have where they are equidistant to several earliest activation sites. But with this, you can already define the gradients. The gradient with respect to the timing is not very difficult. Of course, if you increase the time you start from, then of course all the points in your region of influence will also activate later. So the last question is actually, how do you compute the geodesics? And you can have a simple observation that the Riemannian metric D actually imposes a new scalar product on the domain, which is also given by this equation. But the important takeaway message is here, you can simply pose this simple ODE for each point on the domain or for each point where you want to compute the variation with respect to and solve this. So here's also again a visualization of what you do. So imagine you have X1, which is your earliest activation site, and you're interested, I want to move it in a certain direction. How will this change the activation times on my domain? So you compute the geodesics here in white, and you can already see then that from this, you can compute then the gradient at the source and have the dot product with the normal direction in which you want to move the point. And this makes also logical sense since, okay, I'm moving in direction n, so points which I move away from are activated later. But this is now coupled again with a nice mathematical formulation. So if you have several regions of influence, this is what I was talking about earlier, you can see that each geodesic will converge from the ODE to exactly one earliest activation sites, except for some of the boundary cases, but usually these are negligible. So with all of this in mind, we can pose a first order optimization or minimization problem. We want to minimize, or we want to find the optimal earliest activation sites given some measurements phi hat. So activation times phi hat on some subdomain gamma. And we simply minimize with respect to the quadratic distance or quadratic mismatch using the Hamilton-Jacobi formulation again. So we can use the gradient that we showed earlier. And basically you get now this nice energy functional, which you can re-implement, but I will also give an intuitive explanation of this later on. If you have multiple earliest activation sites, again, you simply need to split the domain, and there's a one-to-one correspondence anyway, so the residuals will only contribute to the earliest activation site that the geodesic is connected to. So here's the intuitive explanations. You first compute all the geodesics from gamma to the earliest activation sites xi. Then you compute the least squares functional, and actually you just have to compute the gradient of the geodesic at the source at the earliest activation site. You weight this then with the residual. So of course, if you have a higher mismatch between your measured and your computed activation time, then this influences the cost functional more. And basically you can use this gradient then in any optimization scheme that you like, gradient descent, Adam. We used Gauss-Newton, but of course the method is not limited to that. And here again is like a depiction of this algorithm. So you can see, for example, on the 2D domain, we have only measurements on the boundary. So we compute all the geodesics to x1. Then we get this weighted residual and the weighted gradient direction. And iteratively applying this, we can actually move our earliest activation sites to the optimal point that reproduces the activation that we measured on gamma. We conducted several experiments. So on the top row, you can see 2D experiments. Again, the square domain with 3 earliest activation sites and the conduction velocity that you saw earlier. And the measurements are only given on the boundary. Similarly, a 2D idealized left ventricle slice. And again, we only got the measurements on the boundary, and we have some transmural fiber variation. Also, we have an in vivo experiment. So during catheter ablation therapy, this is not an electroanatomical map, but the measurements come from an electroanatomical map. And experiment number 4 is actually a lumped Purkinje formulation. together with some measurements on the epicardium, but this is fully in silico. So for the 2D case, actually, the algorithm is doing quite well. We are able to find the optimal points within very few iterations. It works with all of the 3 points, and you also optimize for the correct timings in this case. For the 3D experiment, of course, we don't know how many earliest activation sites are there, and we also don't know the fiber direction. So the fiber direction was actually mapped using a rule-based approach. And then we just optimized with several different number of earliest activation sites. You can see the mean squared error in milliseconds between the measured times and what we compute. And you can, of course, see as you increase the number of earliest activation sites, you also get a lower error. And similarly for the in silico model, here we actually know the ground truth. So here we know we have 6 earliest activation sites, but it's an interesting observation. For example, if you only have 1 earliest activation site, this actually moves like in the metric middle of all the points to minimize the mismatch, and you get a quite good mismatch already with 1 earliest activation site, even though this underrepresents the model. And with the correct number of earliest activation sites, you get a very good fit. So, but now the interesting question becomes, okay, you can increase the number of earliest activation sites, and of course the cost function will decrease. But actually we propose something else, something called the topological gradient in this case. So from the earlier derivation, you could already see that we have the Hamilton-Jacobi formulation. And what now if you actually take a point and you think about what if I split this point? You get actually then this cost function or this new activation map that you see here. So of the 2 new points that are formed from 1 single point, you will only take the shorter one because you take the geodesic, so ergo the shortest distances. And from this, you can also derive the topological gradient. So more details on this are given in the paper, but you can see it's very similar to our previous definition, but now you have the absolute value. So it's not smoothly differentiable, only weakly differentiable. But now still it becomes an interesting question. So when should we actually split? And with the topological gradient, now you got a differential that tells you how much benefit do you have for splitting in comparison to just moving a source point. And here you can again see the figure from before, but now added, you can also see the topological gradient. So basically, since you have the absolute value, it tells you, of course, every point will just receive a smaller timing, basically. So because you move closer to all the points on the domain. So we used this algorithm. We used some heuristic that we defined, but of course you could use something else that basically tells you, okay, what is the benefit of splitting versus what is the benefit of moving? We start with a single earliest activation site, move again to the metric middle of all of the 3 points weighted by the residuals. And then you can see at time instance, so after around 15 iterations, the algorithm, the heuristic actually tells, okay, you should actually split. And this happens 2 times. And actually you can, from this simple algorithm, you can already find, like in silico trials, the true number of earliest activation sites that you really want to have. For the in vivo experiment, we also tried this. So this is a lot more noisy. And also because it's measured in vivo and we have a lot more uncertainties. There's some interesting things happening here. You can also see that a lot of points get constructed here at the top end of the cardiac model. But this could also be a problem related either to the measurements, which are hard to reproduce, or to the thin wall of the myocardium, which makes it difficult to evaluate the topological gradient if you're close to a boundary. So the last extension for GEASI that I wanted to introduce is the extension to ECGs. So we can simply pose the ECG or compute the ECG from the diaconal model using this equation, which is basically, okay, you integrate over the whole cardiac domain, given the intracellular conductivity tensor GI, the gradient of the membrane potential nabla VM, and take the dot product with the lead field of certain lead ZL. And the interesting thing is we now already incorporated our parameter set E in this equation. So how we do this is actually we just take a fixed waveform and shift it by the conal activation time. Of course, you can think of much more complicated or sophisticated models, but for first test, this sufficed in our view. So the interesting thing is now you have a continuous dependence of your conal activation on the waveform. So now you can take the gradient with respect to our parameter set, which again allows us to optimize as a first order gradient-based approach. And then we simply, so you can write this differential here. The interesting thing now is that you actually have the Hessian matrix. So you have to take second order derivatives of your potential function. But we actually have an infinitely differentiable analytical function. So this is no problem in our case, but of course, this also depends on the discretization. For example, what kind of finite element method you use behind maybe. And in this case, you also need to change your cost functional, since now we don't optimize with respect to the activation times, we optimize with respect to the ECG. So for our initial test, we actually use the L2 error on the ECG. This is actually not really robust and has been shown already to be non-robust, but as an initial test, it sufficed for our experiments. And here you can see the setup of the lead fields that we used. So basically we have 3 axis aligned lead fields, and we embed all models in a cube torso. Yeah, and here you can see the domain with different lead fields. So from this, we get our ECGs on the 2D domain. And actually, in this case, we can find a very good fit. But note that in this case, already the optimization becomes much more non-smooth. And also, we had to move the earliest activation science point closer to the initiation side, to the initial points that we assumed, because it's very easy in this optimization to also fall in local minimum. Same for the idealized left ventricle slice. This proved to be a bit more robust. For the 3D case, actually the earliest activation sites that we initially chose were more or less random, but you can see you get a lot of variation, and it takes a very long time in comparison to activation time optimization to actually converge to the activation that you want. You don't get a perfect fit, but at least the ECG looks decent in this case. So let me conclude my talk by saying the Hamilton-Jacobi formulation really allows for a smooth gradient-based optimization of several instances, several measurements that you can think of. And in comparison to the location optimization, the initiation timing optimization, which was also done at the same time in all of these instances, is really very easy in this framework. And also the topological gradient and the ECG optimization really proved to be, to show that the algorithm could really be applied for a multitude of problems. So what we didn't do in this paper, but what is more or less future work, is that we could also optimize for the conduction velocity tensor, since it's also given in the length functional and the subsequent ODE. But on the downside, you could also see that the computing all the geodesics can be very costly, especially since it grows with the measurement domain size. And the second order derivatives of the ECG optimization are also a minor drawback. So for the cost functional, you can really think of much more sophisticated solutions. And this is also what we want to do in the future. So in case you're interested in the paper, you can check it out in arXiv. It's been accepted, but it will be published in a few days. So the version is not online yet. And also, if you're interested in a 2D square domain example, you can find it on my GitHub repository to try out. So thank you for your attention, and I'm looking forward to your questions.
So thank you very much, Thomas, for this very interesting talk. So if you have questions, we have still time before the plenary lecture. I will be the first one. So it was very interesting, the approach where you iteratively, in an iterative manner, you are selecting to split the number of earliest activation times. And my question is related to the last result, the one related to the ventricle. I think, do you think that maybe in this case, this approach is, since there maybe you have the effect of the Purkinje fibers, maybe in that case you should start maybe from more than one instead of wait just to the algorithm to find all the possible split. So I think that already in that case, you start in a configuration where you expect that you have multiple earliest activation time. So so what do you think about this issue here, and how do you think that you can manage to fix it?
Well, I think you're right. So if you have more knowledge about the Purkinje network, this could certainly help, because if you start with one earliest activation site, you're always sure, okay, this will not be able to fit the measurements that I get. I mean, it would be actually surprising if it were able to do so. But if you have a Purkinje network, then I think you would get less variation and also less moving around the ventricle. So I think it would be very nice, and also maybe if you can restrict the Purkinje network entry points to certain subdomains, that would also help a lot. But of course, in this proof of concept, it's more or less like, okay, what does the algorithm do if it has complete freedom of everything? Okay,
thank you very much. And another question is about, okay, no, there is a question from Professor Dirks. So please go ahead.
Yes, hello. It's a very interesting work. I have a question. If you have a periodic arrhythmia, like a VT or something, could this method to be extended to find like the position of the rotor or something?
Well, we already discussed this. It would need, I think it would need some modifications, because in the original iconal formulation, it's actually, you can't really have periodic effects, since you usually only compute the earliest activation times. But nonetheless, you could still try to compute the earliest the activation times differences that you have on the domain. And, you know, if these mismatches are too large, you can actually, you know, locate at least rotaries, I think. But this hasn't been tried out yet. So it was just an idea that we threw around in the past.
Okay, but still, yet it is very powerful and already has good applications. So it's excellent work. Thank you.
Thank you.
So thank you very much. Unfortunately, we ran out of time.